Hello everyone. Just letting you know, so I started recording one of these videos, but I realized I had it in vertical mode, and that would be obnoxious. And so I'm starting over. Unfortunately, you won't get to see me write this problem. But today we're doing optimization problems. So we're going to do 3 examples, and then I'm going to give you 1 example to work on your own. And then the Monday after spring break, that's what we'll start with just a solution to it. I do recommend do the problem on your own, or at least attempt it first. So this first problem, a Norman window is constructed by adjoining a semicircle to the top of an ordinary rectangular window. Find the dimensions of one such window of maximum area if the total perimeter is 16 feet. If you need to copy that, press pause on this video, but I'm just going to keep moving on and solving it. So what you want to think of is you have a rectangle with a semicircle on top. All right, and so what we want to do is we want to maximize the area if the perimeter is 16 feet. The dimensions we might want to do is this up here is y, and then this whole length is x. So those are our dimensions. All right, so if we go back up here, we ask ourselves, what is the thing we are trying to maximize or minimize? And we can see it's the area. So we're going to call that A for area. So let's do this real quick. So maximize area A by adjusting the dimensions. So those are x and y. So our goal here is to find A prime, which equal to either the derivative of A with respect to x or the derivative of A with respect to y. It doesn't really matter which variable we end up taking the derivative of with respect to, but we do want to just pick one. There is a way to use implicit differentiation, but sometimes that makes things more complicated. So our goal will be just to get A in terms of either just x or just y. So if we look at this, we have a semicircle and we have a rectangle. And so the area of this is going to be the area of the rectangle plus the area of the semicircle. And the area of the rectangle is going to be x times y. And then the area of a semicircle is going to be 1/2 of pi r squared. So if we're looking at the semicircle, we need to figure out what our radius is in terms of x and y. And if we look at this rectangle, our radius length is going to be this right here. But by observing that, we can see that it's actually x over 2. It's half of x is our radius. So when we go back over here, we put x over 2 squared as our area. X over 2 squared. So now we have an area in terms of x and y, but we just want one of them. And so what can we do to replace x or y? And so far, like the hint is, we've used area, but we have not used perimeter. And so our perimeter is 16 feet. And so we want to look at going around the entire window. And so by the perimeter, I mean only the outside. We're not going to include that piece going across right here. So only this length. And so our perimeter, which is 16 feet, is going to be this side plus this side plus this side. So that's 1x and 2y. And then this length right here. And so this is half of the circumference. And so the circumference is 2 pi r, and half of 2 pi r is just pi r. And again, our radius is just x over 2. So the circumference is going to be pi times x over 2. All right, so we can either choose to solve for x or to solve for y and then plug that into our area equation. As far as like choices go, I think solving for y is going to be easier. And it's only one thing to replace over here, so I think that's going to be my choice. However, it can be x. It doesn't really matter. And so let's see here. So I'm going to subtract, so 16 minus x, and then minus pi over 2x, so I just rearrange the pi times x over 2 is equal to 2y. And then I'm going to divide by 2. And so that's going to end up being 16 divided by 2 is 8, minus 1/2 x minus pi over 4x equals y. It was divide each factor or each term by 2. And then we go back to our area and we're going to replace this y with this function. And so we get a is equal to x times 8 minus 1/2 x minus pi over 4x, and then plus 1/2 pi. And then let's just square this x over 2, and so that's going to be x squared over 4. All right, so we get this new equation, which we want to take the derivative of. Before we differentiate it, let's simplify it. And so a is going to be equal to, let's see here, so this is going to be 8x minus 4x squared. Oh, what on earth am I doing? It's minus 1/2 x squared. Whoops. Okay. Oh, also, you know how sometimes in class I make mistakes and students call me out? That's still going to happen, but you guys won't be able to call me out in time. So if you notice I've made a mistake, please leave a comment on this video so that other students can look through and see if there's anything there that needs to change. But continuing, so minus pi over 4 x squared. And then I'm going to combine this, and so it's going to be pi over 8 x squared, so plus pi over 8 x squared. All right, we could end up combining our x squared things, but I don't know, I'm feeling kind of lazy right now, so I'm just going to leave it as is and take the derivative. So a prime is equal to 8 minus x minus pi over 2x plus pi over 4x. All right, so there is our derivative. And remember, our goal is to find the maximum area. So we want to set this derivative to 0, or also find where the derivative does not exist, which we don't have to worry about for this problem since it is a polynomial. So let's just set our derivative equal to 0 and solve. So 0 is equal to 8. And I'm going to combine these. So it's going to be minus 1 minus pi over 2 plus pi over 4. And so that's going to be plus, and then I'm going to combine these things. So it's going to be minus 1 minus pi over 4 when you add these together. So minus 1 minus pi over 2 plus pi over 4 is this, times x. And so then, let's subtract 8 to the other side. And you have minus 1 minus pi over 4 times x. And then if we divide negative 8 by this guy, you end up with positive 8 over 1 plus pi over 4 is equal to x. All right, so this is our potential. And then I just want to plug that into a calculator and see what that is. Let's see here. All right, we've come into an issue. So I use my phone as my calculator, but I'm also using it as my camera, and I don't know how to do both at once. So I would do that for yourself and find out what that approximately is equal to, but this is a good answer. Again, it's not our final answer because we need to check that it's a maximum. And so we can either do a first derivative test or a second derivative test. Since this is such a simple first derivative, let's use the second derivative test. And so we're going to do our check. So our check. And we're going to do it with the second derivative. So when you take the second derivative, I'm going to use this form of the first derivative. We're just going to be left with negative 1 minus pi over 4, which, if you notice, that is a constant function. And so if you were to plug in our 8 over 1 plus pi over 4 into this, then you just get negative 1 minus pi over 4. Therefore, our second derivative is negative, so our function is concave down, and we have a maximum. So that's good. And so to find our maximum overall, we would just plug that into the original equation. So the maximum would be, and then our original equation would be this area, or it's actually asking for the dimensions on this one. So we don't actually find the dimensions of the window. So we don't actually have to find the area based on what the question has asked. It's just asking for the dimensions. And so we got our x, and we need our y. And so we could say that our x, so if we go back down here, so the dimensions would, would be x equal to 8 over 1 plus pi over 4, and y is equal to, and then you would solve this, and so it'd be 8 minus, and let's say it's 1/2 plus pi over 4 times 8 over 1 plus pi over 4. Whatever that would end up being. So I'm just plugging, first off, I simplified this equation. I factored out an x, and then replace the x with our actual value. So we just solve for y, and that would finish the problem. Okay, so this has been the entire problem. We first identified we needed to maximize the area. We then came up with an equation for the area in terms of the dimensions, because those are the things we're adjusting. We then used other information to replace one dimension with the other. So we replaced our y in terms of x's using our perimeter, set the derivative equal to 0, and solved for x. And then we checked that that dimension gives us a maximum and not a minimum or something else. And then we finished the problem by giving both dimensions. Okay, so that is problem number 1. So let's start on problem number 2. Oh, I'm going to flip this way, I think. So example number 2. All right. So what was the one I wanted to do second? Oh, this one's fun. Okay, so this is a classic example of a type of problem that you will see in optimization. So a man in a boat. So a man in a boat, 2 miles from the nearest point. Oh, this is kind of hard holding the camera and writing at the same time. Okay, from the nearest point on the coast. Oh, this should be an is here. A man is. There we go, that's a sentence. A man is in a boat 2 miles from the nearest point on the coast. He is to go to a point Q located 3 miles down the coast. So he is to go to a point Q 3 miles down the coast. And 1 mile, so that's 1 mile, inland. He can row at 2 miles per hour and walk at 4 miles per hour. And walk at 4 miles per hour. Toward what point? So toward what point on the coast? Toward what point on the coast should he row in order to reach point Q in the least time? Okay, so here's the whole problem. A man is in a boat 2 miles from the nearest point on the coast. He is to go to a point Q 3 miles down the coast and 1 mile inland. He can row at 2 miles per hour and walk at 4 miles per hour. Toward what point on the coast should he row in order to reach point Q in the least time? So you guys have actually kind of thought of this problem before. If you have ever cut across the grass on campus. Like maybe going across the grass would mean that you walk a little bit slower than on the sidewalk, but you go less distance. And so that is the idea here with this one of you may go slower in the water and faster on land, but you don't necessarily want to go straight to the land and then walk the whole way. And so let's do this picture here. So here's our coast. And here is our point Q. So it is 1 mile inland, and then 3 miles this way, and then here is U. And so this is 2 miles. This is 1, and this whole distance here is 3, right? So 2 miles, 3 miles, and then 1 mile. The path you would take, however, would be something like this. Like you would row at an angle and then walk at an angle. And so what we want to do is we want to minimize this distance. And so we're going to want to take this distance and this distance, and we're going to want to minimize those. So minimize, and let's say that, what would be a good letter? Oh, let's just say C. So minimize total distance. C equal to A plus B by adjusting. All right, and the thing we're adjusting is this point right here. This point right here. So let's say that this distance is X. All right, so by adjusting X. All right, so we're minimizing the total distance by adjusting X. And so let's set this up. So if you look at it, you get two classic right triangles. So the guess that we're going to be using is the Pythagorean. And so we have this distance is 2, this distance is 1, this distance is X. And then if we look at this distance right here, the total distance is 3. So this distance is going to be 3 minus X. And so if we were to set up our equation, it's going to be C. So the total distance is going to be the distance of A. So we're going to use the Pythagorean theorem. So A squared equals 2 squared plus X squared. So A is equal to the square root of that. So it's going to be the square root of 4 plus X squared. So that is distance A. So just using the Pythagorean. And then we're going to plus our B. So this is A. And then our B is going to be B squared is equal to 1 squared plus 3 minus X squared. So B is equal to the square root of that. So we've got the square root of 1 squared, which is just 1. And then plus 3 minus X all squared. All right, so this is our distance. You know what's really nice about this? There is only x's here. We don't have to do any replacement, so we just need to take the derivative. And so I'm going to rewrite this. So C is equal to 4 plus X squared to the 1/2 plus, and then we have 1 plus 3 minus X squared. You know what? I think I'm going to distribute that. And so when you FOIL out the 3 minus X squared, you should end up with 9 minus 6x plus X squared, all to the 1/2. Okay, so This 1 plus 9 will give us 10 whenever we go through and take like the derivative, so just know that that's going to change into 10. And so C prime is equal to 1/2 times 4 plus x squared to the negative 1/2. So that's the outside, and then times the derivative of the inside, which is 2x, plus, and then we have 1/2 times 10 minus 6x plus x squared. Oh, I do this every time. I don't give myself enough room. Times 1/2 times the derivative of the inside, which is 2x minus 6. So times, I'm going down here, 2x minus 6. And so the derivative is this nasty looking thing, and we're going to set it equal to 0. When I set it equal to 0, I'm also going to put those square roots on the bottom, just because I think it would be easier to solve that way. Okay. This is going to require a lot of algebra to finish this problem. So, yeah, we might end up spending a little bit more time on this to finish solving. All right, so let's rewrite this. So C prime, oh, I want to go down here where I have more room. So C prime is equal to, and when we rewrite it, it's going to be x over the square root of 4 plus x squared. So that's just this piece right here. So 1/2 times 2x is x, and then move this to the bottom in a square root, plus, and then here 1/2 of 2x minus 6 is just x minus 3. So we have x minus 3 over the square root of 10 minus 6x plus x squared. So here we go. This is what we have. So our first step, we need to find. So find where C prime is equal to 0 and C prime does not exist. That is our goal here, is to find where C prime is equal to 0 and where C prime does not exist, because those are the places where we could have a maximum or a minimum. So if we look at this, this guy does not factor. The only factors of 4 plus x squared is 2i and negative 2i, if you were to solve that with a quadratic or by just squaring it. So we don't care about those. And then this guy factors, let's see here. So 10 can factor into 2 and 5. So this is going to end up being something we'll need to solve with the quadratic. And so let's just go through and see if we can. So x is equal to negative b, so that's 6 plus minus the square root of b squared, which is 36, minus 4 times AC, so minus 4 times 10. Oh, hey! All right, we don't even have to finish this, because this guy is 36 minus 40, which is negative 4, which means it is also imaginary. So, also imaginary, so we don't have to worry about it. So also imaginary, don't worry about it. Oh, and just to finish this so you're not confused, so it's over 2a. So over 2 times 1. Okay. That negative 4 is not part of like the actual quadratic formula. But yeah, we're good. There's no place where it does not exist on the real number line. So we just need to set it equal to 0 and solve this lovely equation. So we're going to keep on going. So 0 is equal to, and we want to have a common denominator. So we're going to pick the simplest option of the common denominator is just this denominator times this one. And so if we want the common denominator here, we're going to multiply x times this denominator. So we have x times the square root of 10 minus 6x plus x squared, plus, and then we have x plus 3 times this denominator, which is the square root of 4 plus x squared. All right, all over, and then we have the square root of 4 plus x squared times the square root of 10 minus 6x plus x squared. Okay. All right, so we have this. But remember, when we multiply it by the denominator on both sides, 0 times the denominator will still be 0. So really, we only have the top that we're working with. Again, it's not fun at all, but we can do it. We can do it. What I would probably, All right, so I think this is going to be part 1, and I'm going to do the algebra off camera and post part 2. I don't know how to edit things together yet, so you're just going to have to be patient. And then I'll also give you the problem that you want to do. I've decided just to do 2 problems because I think a third would take too long. Actually, I'll do the third problem off camera, and I'll put it up in the second video so you can pause it and look at it. And then I'll give you a problem in the second video. But I think this is where I'm going to stop. But please, please, please click on the second video.